So, schönen guten Tag. Ich begrüße Sie zur nichtlinearen Optik. Well, in English, I guess. But I think the greeting is okay also in German. Well, it's about the coupled wave equations, isn't it? And we derived this equation that has here the house number 15. So you see it's a driven wave equation. We still have here the derivative, the temporal derivative. But if we assume that we are dealing with monochromatic waves, then of course we can do this, derivation. And if we do it, then of course we get this factor of omega n squared, where n runs here, say, from 1 to 3 or 4, depending on whether we have 3-wave mixing or 4-wave mixing. So the next point was that we said, well, let's specialize to some frequency generation. And we would calculate in particular the situation for the field E3, namely for the sum frequency. So we assume that the two incident frequencies, the two incident waves, that this is omega 1 and omega 2 with amplitudes E1 and E2. And now we are particularly interested in what happens to the sum frequency E3. So, and the equation for that is this equation 20. Yeah, so we did basically nothing, we just specified here the index. Okay, well, then we said, suppose that the right-hand side is actually 0. Then we would know, of course, the solution. It's a wave equation, and therefore the solution is a wave. And this is actually written here. And the next point in our reasoning was that we said, well, if the right-hand side is not exactly 0 but small, then we would say, well, then this is probably not the solution because it was the solution without this here, but it's almost the solution, yeah, because the right-hand side is assumed to be small. And then it makes sense as a physicist to think about what's going to happen and what we want to see and what we expect. And of course, we expect that the amplitude of this field, that this changes. If we generate the sum frequency, then obviously the sum frequency, the amplitude of the sum frequency will increase. We'll see whether it can only increase or also decrease, right? Anyway, okay, so the next step is also clear. Namely, we need, yeah, so we have now an ansatz for this wave, but we also need one for this here, right? We know from our Taylor series expansion of the polarization that it kind of looks like this. Yeah, so formally, instead of this D effective, we wrote the susceptibility, and of course this D effective has something to do with the susceptibility. We'll come to it at a later stage of this lecture, but just to give you an idea, suppose you have a crystal and you orient it in the one position or the other position, then of course the susceptibility, which is, as we know, a tensor, will have a different influence. And in order to avoid these tensors, one kind of condenses the action of the susceptibility tensor into the scalar, provided that the geometry is predefined. Yeah, so for predefined geometry, for a predefined orientation, we can just write this susceptibility tensor as a scalar. And this is what I did here. Okay, now let's go on. Of course, we know that E1 and E2, that these are fields, and we just write the respective expression for that. So let me do that. So we would know that EI of Z and T, that this is equal to the amplitude times its temporal evolution, plus complex conjugate, of course, and the EI, so we split off the spatial dependency in this amplitude EI, right? So we have here I, K, I, Z. So this is supposed to be equation 25. And if we put that all together, then we get an expression for the polarization. So what we do is that we plug 25 into 24, and then we find that P3 is equal to 4 times epsilon 0 times what's called the effective nonlinearity, A1 times A2, and then this expression for the spatial dependence. So K1 plus K2 times Z, and sometimes I abbreviate this, well, all these prefactors with P3, and then it would be P3 times e to the I K1 plus K2 times Z. So that's equation 26. Okay, so what we want to do now is to substitute all this into our equation 20, so into our driven wave equation. And to this end, I would write equation 20 once again. So what we want to do is to substitute equation 22 and 26 into equation 20. Substitute 22 and 26 in equation 20, and I write it down once again, namely, and I do it in colors because we will evaluate it term by term. So then plus now some green color here, n3 squared divided by c squared, and well, I still have here the derivative. Well, doesn't matter. So we do it this way, and this should equal minus 1 over epsilon 0 times c squared, and the second derivative of the nonlinear polarization. Right? So, so this is, so now we evaluate term by term. And we start with the red one. So the first term so this is a second derivative. This makes actually most of the work. So we have the second derivative of, well, a plane wave, and therefore this reduces just to a simple derivative. Instead of the Laplace operator, I can just write the second derivative with respect to z. And then I have to plug in. So I get minus the second derivative of a3 of z times e to the I k3z minus omega 3 times t plus the complex conjugate. Right? And doing this derivative is actually straightforward. I just give the result here. We get, of course, the second derivative of the amplitude with respect to z. We get from the mixed terms, we get 2 times ik3, and now the first derivative of a3 with respect to z, and then a term with no derivative. And we have e to the ik3 times z minus omega 3 times t plus the complex conjugate. So now to the next term here. So the second term, which I have in green color here, is of course very simple because it's just a temporal derivative. So what we have here is n3 squared over c squared, and then the second derivative of e3. And because it's just sine-like thing, this is very easy. So we have minus n3 squared divided by c squared, omega 3 squared. Yeah, so the minus sign comes from the imaginary unit square, and omega 3 also from the chain rule. And then we have a3 e to the ik3 times z minus omega 3 times t plus the complex conjugate. Yeah? And finally, the third term, similarly easy. There we have minus 1 over epsilon 0 times c squared, and the second derivative of the polarization, so the acceleration. And this would give minus 1 over epsilon 0 times c squared, and then the second derivative of p3 times e to the minus I omega 3 times t. Yeah, so the spatial dependencies, they are hidden in P3. Well, and we can, of course, easily do these derivations. And what we get is plus omega 3 squared divided by epsilon 0 times c squared times 4 times epsilon 0 times the effective nonlinearity times a1, a2, and then e to the I k1 plus k2 times z minus omega 3 times t, well, like this here. And of course, also here the complex conjugate. Yeah? And now we have to take, we have to sum these three terms together. Yeah, a lot to write, but not really demanding. So together we would have, so from the first term, so we have the second derivative here. So the second derivative of a3 over dz squared, then plus 2ik3 times the first derivative of a3, and then k3 squared times a3. So then the second term, so there we have n3 squared divided by c squared times omega 3 squared, and then a3. And now the exponential. And then we would continue with the right-hand side. So the complex conjugate, of course, is also missing. And now the right-hand side, we have minus 4 times d effective omega 3 squared divided by c squared, a1, a3, and e to the I k1 plus k2 times z minus omega 3 times t, and the complex conjugate. So, what can we do now? What would you do next? So if you look at this here, no idea? Well, so look at these two terms here. Yeah, so K3 or K is omega divided by C, right? And therefore K3 squared is omega 3 squared divided by C squared. And actually K is n times omega divided by C. Yeah, so these two terms, they cancel. Isn't this nice? Yeah, so they cancel. I wanted to have it in red. So, like this. Yeah. Now, what else could we say? What else could we say? So you probably think about getting rid of this term here, of this I to the omega 3 times t, right? So which seems to be here and here. But there's one thing that that is not so nice. You can't just drop it because there's also the complex conjugate. What can we do? Why can't we drop the complex conjugate? It's right that we can drop the complex conjugate. Well, actually, this is not just one equation. These are two equations. Because the complex conjugate and, the original version, they are linearly independent. So this equation must hold for the complex conjugate and, the rest independently. Yeah. So let's write that down. So we can drop the complex conjugate. Because e to the I omega t and e to the minus I omega t are linearly independent. So let's drop them. Yeah. So the CCs are gone. Yeah. And then, as I said, we can also drop the factor e to the minus I omega t. Yeah, so once the complex conjugate, let's just write, once the CC is gone, we can divide through e to the minus I omega 3 times t. Yeah? And This then gets us rid of this thing here. So maybe I should have done it in this way. Okay, so then our equation looks much nicer. Namely, we have now the second derivative of A3 over the second derivative of A3 plus 2 times ik3, first derivative of A3, with respect to z, e to the ik3 times z is equal to minus 4 times this effective nonlinearity omega 3 squared divided by c squared. A1, so please remember that A1 and A2 also depend on z. And then e to the ik1 plus k2 times z. So that's equation 27. Yeah, so what do we do now? Maybe something for my poll everywhere. Doesn't work again. So, does it work? First the test. This stupid thing here. Okay. Well, so equation 27 would be hard to solve. What shall we do? So your ideas? Doesn't work?
Doesn't work.
Oh. So does the first one work? No? Okay, bad luck. Okay, nevertheless, what can we do? What would you do in order to find some solution? So the equation, the differential equation is too difficult. What would you do then? No idea? Well, you could give a generic answer. What would be a generic answer to this? Yeah?
Some simplifications, approximations.
Some approximations, yes. Yeah, so some approximations. So now let's look at these terms and see where we could start with an approximation. It helps, of course, if you think about the physics that's going on. Yeah, so usually this is a good strategy, yeah, to think as a physicist and not as a mathematician. So we have 3 terms, right? Which one would you target? What is A3? How big is A3? Compared to A1 and A2? Probably small, right? Because if it would be large, then we would see nonlinear optics all the time here in our world, but we never see it. Yeah, so we need a laser in order to see it. So A3 is is probably small. Yeah? If A3 is small, then also the derivative is small, isn't it? And the second derivative is even smaller. Yeah? Here we are. Yeah? So what we do is that we do what's called the slowly varying amplitude approximation. Actually, this kind of approximation is also done in quantum optics in a different context. Yeah, so the slowly varying amplitude approximation is not unique to nonlinear optics. Okay, yeah, so 11. Next point here. The slowly varying amplitude approximation. Amplitude approximation. It even got an abbreviation, an acronym, namely SVAA. So we neglect the second derivative. Yeah, because A3 is small, which means that the derivative is also small, which means that the second derivative is even smaller. Yeah, so this is the change in slope, right? So the first thing that we're interested in is how A3 grows. And this is described, of course, by the first derivative, right? And here we have only, well, the next order thing that could happen. Yeah? Of course, you can also, be a little bit more serious than I am, and really quantify when this holds. Yeah? And this is actually also quite easy. You just need to look at these two terms and compare them, right? And if this is much smaller than this here, right, which basically means that over a wavelength or so, the change in amplitude is not very pronounced. Okay, so now we use the slowly varying amplitude. Yeah, so with the slowly varying amplitude, our equation assumes the form we have 2 times I k3 times the derivative of A3 times e to the I k3 times z is equal to minus 4 times the effective nonlinearity omega 3 squared divided by c squared, and then A1, A2, e to the I k1 plus k2 times z. Yeah? Well, we will manipulate this equation a little bit because we are interested in particular in what are we interested actually? Yeah, and this would stand on the left-hand side of the equation sign. Yeah. We are interested in A3, yeah, or the change of A3. So we just solve for A3 or for its derivative. So we would get A3, the derivative of A3 is equal to I times 2 times the effective nonlinearity times omega 3 squared divided by c squared k3 A1 A3 times e to the I and then k1 plus k2 minus k3 times z. Right? And this thing here is important, this exponent here. We will call this here delta k, and delta k has a name. It's called the phase mismatch, or momentum mismatch, wave vector mismatch. So phase mismatch or momentum mismatch, or sometimes also wave vector mismatch. Mismatch is the important thing here. Yeah, we can of course substitute or simplify this further by noting that k is n times or n3 times omega 3 divided by c, right? And then one of these omega 3 cancels. So using k3 equals n3 times omega 3 divided by c, we find that dA3 over dz is equal to I times 2 times the effective nonlinearity, then just omega 3 divided by c. One cancels with this k3. And then we have n3, and that's it. A1 times A2 times e to the I delta k. So this important factor here times z. So that's equation 28. Yeah. And with this, we are actually done. So this is a coupled wave equation. We would do the same thing. For the other equations. So for the other amplitudes. So doing all these steps that we did here, starting here, here. So we would do the same thing, or even a little bit earlier. So, well, basically the same procedure here for A2 and A1. And then we have the full set of coupled wave equations. So, 13. Do the same thing also for A1 and A2. I don't do it here. I just write down the result. Then we get dA1 over dz is equal to I times 2 times the effective nonlinearity, omega 1 times, squared. Yeah. So this is actually wrong here. So what I meant and what I probably said was omega 3. And the same mistake here. Squared divided by k1 c squared. I'm not sure why I write here k1 again, but never mind. Then we have A3 and here A2 star. So if you do this calculation, and e to the minus I delta k times z. Then the next one here, A2, the derivative of A2, this is I times 2 times the effective omega 2 squared divided by k2 c squared, A3, A1 star, e to the minus I delta k times z. And the one that we derived actually, I just write it here in order to make it complete. So we have here the effective nonlinearity again, k3c squared a1 times a2 times e to the plus I delta k times z. Right? And what you should always keep in mind is that, of course, a3 and a2, they also depend on z. Yeah, so you see that these equations are really coupled in this sense here. Right? So it's of course clear that this here depends on z. So these are the coupled wave equations. Yeah, and they deserve a fat, yeah. Can I have this more beautiful? I guess so. So like this. Yeah, so these are the coupled wave equations. Let's write that down. Yeah, so these are the coupled wave equations. Coupled wave equations for some frequency generation. Right? For other nonlinear processes, they would look a little bit different. Good. Well, what should we do with these coupled wave equations? Solve them, right? And of course, we start with a few trivial cases. Yeah, and they actually run under the headline of phase matching considerations or phase mismatching considerations. So we will do actually both here, that we will have a look at phase mismatch. Yeah, so in particular, so this means we are interested what this guy here is doing. Yeah, so this delta k. Yeah, so if it is 0, then we would speak of perfect phase matching. If it is not 0, well, then we have a phase mismatch. And in doing so, we find actually the first, the first kind of solutions, trivial solutions for that. But the headline is, as I said, so this is 3.4 phase mismatch considerations. Yeah, we solve this equation for a simple situation, namely for kind of this situation that we already discussed. Yeah, so we want to look only at the sum frequency, and in the spirit of what we said, and actually driving this to the extreme, we say that A3 hardly changes. Yeah, so that A3 really remains small. What can we then say about A1 and A2? Yeah, so if A3 is, say, just 10 to the minus 4 or so of this amplitude here, what can we then say about A1 and A2? So in particular about its dependence on Z. No idea? Yeah?
You could assume that it's constant.
Yeah, then they are constant. Yeah? So if A3 remains small, so if there are just a few photons in A3, then of course not many photons of A1 and A2 are destroyed, so the amplitude remains constant. Yeah? Yeah. So let's write that down. So we assume that A3 remains small as compared to A1 and A2. Yeah? And this immediately means that A1 does not depend on Z. Yeah? And the same thing for A2. Yeah, and then this differential equation is really nice. Yeah, so what we then have is that D is, doesn't look much different as compared to what I had before, but now the right-hand side does not depend, well, very much on Z. Well, probably I have to take that back, because we have here this thing, this exponential with the phase mismatch, which still depends on Z, right? But what we could say is that this equation here is not easy enough, not simple enough. We make it even simpler. We just assume that we have perfect phase matching. Yeah? Then delta K is equal to 0. Let's do that. Yeah? So we are really lazy today and make life as simple as possible. So this differential equation can actually be integrated immediately, because integrating an exponential is not very difficult. But nevertheless, so we take it easy. So in order to make things even simpler, assume perfect phase matching. Phase matching, which means that delta K is equal to 0. Right? Well, what can we then say about A3? What then about A3? Yeah.
The derivative is constant, it increases linearly.
It increases linear, but wait a minute, it increases linearly? Aren't we here in nonlinear optics, and it increases linearly? I would have expected something nonlinear. Well, I'm joking, yes? Because we are talking here about the amplitude, not about the number of photons. Yeah, so the number of photons is proportional to the intensity. Yeah, and if the amplitude grows linearly, you are, of course, completely right, then the intensity increases quadratically. Yeah, so it is nonlinear. Okay, yeah, so what we then get is that A3 of Z increases linearly. And this means the intensity I3, which is proportional to A3 squared, increases quadratically. Good. So that was really simple. But we have to do the case where phase matching is not equal to 0, because after all, the headline is phase mismatch considerations. So we should look at this case. Yeah. So now the case delta k not equal to 0. Yeah, so the differential equation can easily be integrated. So integrate the above equation, and then we would get Z after some propagation through a certain crystal of length L. Right? So we assume that we integrate along the path of the beam through the crystal. And the crystal has length L. Yeah? So what we would get is, so we have all these constant factors that we can factor out and write in front of the integral. So we have k3 times c squared. A1 and A2, they are supposed to be independent of Z. And then we integrate from Z equal to 0 to Z equal to L, e to the I delta k times Z. Right? And as I said, the integral can be done immediately. And what we get is 2 times the effective nonlinearity, omega 3 squared. Yeah, so all these prefactors, a little bit annoying to write them down all the time. E to the I delta k times L minus 1 divided by I times delta k. Yeah, that's equation 31. Yeah, so now we want to see what this delta k is doing. Yeah? And to this end, we calculate the intensity. So in order to see the effect of delta k, in order to see the effect of delta k not equal to 0, we compute the intensity I3. Yeah, and the intensity is given by, well, it's proportional to the amplitude squared. Specifically, it is c times n3 times the field constant divided by 2 times now the amplitude squared. Yeah? I write the magnitude because generally it's complex. Yeah? Do you remember actually this formula? Yeah? So that you have to multiply basically by c times epsilon 0 divided by 2. Yeah, so you know these things by heart? I don't. I remember it actually in a different form. Do you know actually what c times epsilon 0, which unit this has? What is the unit of c times epsilon 0? And how big is it? So this is actually 1 over 377. Now what? Ohms. And this fits very nicely. Yeah? So because if we know, of course, that the electric field is given by volt per meter, so we have volt squared per meter squared, right? And now if we divide through ohm, so 1 over ohm, then we have volt squared divided by meter squared, and then this thing here, right? So you see that this here cancels. Then we have volt ampere is watt, right, per square meter. Here we are. Yeah, and the 377 ohms. What is this actually? Yeah, everybody here had a course in electrodynamics in the second semester and in the third semester. This is the impedance of vacuum. Yeah? Okay, so take the square of the amplitude and divide it by 2 times the impedance of vacuum, and you are there. Yeah, of course, you have to use also the refractive index if it is not in vacuum. Okay, anyway, just a small excursion. So now we have to calculate this thing, but yeah, so I don't want to do it in all details. I just write down the result. 2 times epsilon 0 times the effective nonlinearity squared omega 3 squared divided by Cn3, and then we have the amplitude of A1 squared, the amplitude of A2 squared, and we have, well, this term here with the phase mismatch divided by delta K, also squared. Yeah? So that's equation 32. I'm not sure whether you would, well, recognize something at this expression here, this one here, right? So the interesting stuff happens here because this here is dependent on delta K, right? All of that here is constant. So this is boring. We just need to look at this thing here. Does anybody see immediately what this thing here is doing? Well, I wouldn't, so I would have to do it by hand. And, well, yeah, so you see it's the amplitude, it's the magnitude squared of a complex thing. Yeah, so we should get something real out of that. Well, again, I don't want to do it in all details. You find it in the script. But what comes out is actually a nice function, namely the sinc function squared. Yeah? So this thing here is the sinc function squared. Yeah, so, and I write it actually in this form. Yeah, so e to the I delta k times L minus 1 divided by delta k squared. This is L squared times sinc squared times L over 2. Right. Well, what we can now do is, in order to do a complete job, we can also replace this here by the intensities, right? So this is proportional to the intensity I1, and this here proportional to the intensity I2. So, yeah, so after a few steps, one finds this here. So next thing would be that we use that I1 is equal to C times N1 times epsilon 0. Once again, C times epsilon 0, this is the inverse of the vacuum impedance. Yeah, 377 ohms, which is easy to memorize in contrast to the rest. So we use these two things here, C times N2 times epsilon 0 divided by 2 times A2 magnitude squared. Right? And then we get that I3 is equal to, again, I skip a few steps here, a few trivial steps. So A times the effective nonlinearity times omega 3 squared times I1 times I2 divided by N1 times N2 times N3 C cube and epsilon 0. Then the length of the crystal, L squared, and here the sinc function, delta K times L divided by 2. Yeah, so once again, if we would have perfect phase matching, right? So then this thing here would, this sinc function here would converge just to 1. Yeah, so this would here, this part here would be 1, and we would recover what we said before, namely that the intensity increases as well as the length of this nonlinear crystal increases. Yeah? So we would have the same thing, so we reproduce what we said in the beginning of this subchapter. Right? And but now if we don't have good phase matching, then after a certain length of the crystal, the intensity will go down again, right? And it behaves like a sinc function. I brought with me a plot, but it doesn't work, unfortunately. Yeah, so if we plot it like this, this sinc function, then it looks kind of like sinc function squared, something like this here. Yeah. So what you see is that once the argument of the sinc function gets greater than a certain value, yeah, so you go down this curve here and the intensity here goes down, right? And actually, so people say when L is equal to 2 divided by delta K, right? So then the argument here is 1. The newly generated wave gets out of step with the generating wave, right? And therefore it's called the coherence length. Now, it has nothing to do with the coherence length in linear optics. Now, it's unfortunate that it's called coherence length. Now, one could have called it the phase mismatch length or something like that. But they called it the coherence length. Why did they do this? Just some speculation. So actually, nonlinear optics was, to a large part, well, developed by electrical engineers. And they just had no clue of optics, I say, right? So they probably didn't know that coherence length was already given to some other phenomenon, I guess. Yeah? Well, actually, one has to say that many physicists were just too arrogant to look into nonlinear optics. So in the 60s or so 50s, 60s, and so on. Yeah, so the physicists they just dismissed optics as something from the 19th century, and what was modern then in physics? Particle physics, of course, and nuclear physics. Yeah, yeah, times change, right? Yeah. Okay, so L equals L coherence and defined as 2 over delta K is called the coherence length. Good. So you learned something very important about phase matching, right? And whenever we talk about phase matching, you always have to think about the sinc function. Yeah? So at some later point in this course, we will look at phase matching again and calculate things like what's called the tuning curves. But you will find this sinc function there all the time. Okay, so next subchapter. So we did a really rough approximation, didn't we? So we said that A1 and A2, they just don't depend on Z. And now we will just do the other extreme. We say we consider this thing here in its full spatial dependencies, right? So no approximations any longer. And what we'll find is what's called the Manley-Rowe relations. So 3.4, no, 3.5. This was 3.5. Chapter 3.5. The Manley-Rowe relations. Yeah, so one should think that they were invented by two people by the name Manley and Rowe, and this is actually true. But actually I only found more information about Rowe. Maybe we switch to the slides. So here you see him as an old man. Yeah, so he died in 2018. And, well, I had to look quite a while in order to find something about him. And finally I did. Yeah, so he celebrated apparently his 90th birthday here with his family. But he was still active on Facebook at that time, right? 1 year later, sadly, he died. And actually, the Manley-Rowe relations, they were not developed for nonlinear optics. They were developed for electrical engineering. And actually, many equations that we have in nonlinear optics, they are kind of familiar to electrical engineers. And he was interested in nonlinear electric circuit or electronic circuitry and how energy transfer takes place there, right? Together with Manley. I didn't find any photo of Manley. Yeah? I think we physicists are more proud of our traditions and of our heroes, and so we know them. Apparently not so in engineering. Okay. Anyway, but meanwhile, you find actually a Wikipedia article of Rowe. Okay. Yeah. So, yeah. So in section 3.4, we looked at the simplest case. where A1 of z and A2 of z were constant. Yeah? To a good approximation at least. Yeah? So we will drop this simplification entirely. And this means we will allow energy transfer between the three waves. We will allow energy transfer between the three waves. Yeah, and we do it actually, we look not at the amplitudes, we rather look at the intensities. Yeah? So, so the intensity, as we discussed already, is given by the intensity of the wave is given by c times ni times field constant divided by 2, and then ai star times the complex conjugate. Okay, now we calculate also the derivative. Yeah? So then the derivative is, well, the change of the intensity with respect to propagation distance, and we have c times ni times epsilon 0 still. And then we have ai star and the derivative of ai. So what we have to use is, of course, the product rule plus ai times the derivative of the complex conjugate. And this can be written as c times ni times epsilon 0 divided by 2 ai star and the derivative of ai plus the complex conjugate. So this we would plug into our equation, into our coupled wave equation. Yeah? So plug this into coupled wave equation, which is equation 30. Yeah, so the first one here. Yeah, so where do I have them? Yeah, so this is actually, they need house numbers. 30A, 30B, 30C. Now, if we do this, then we get, for the first one, we get, a lot of prefactors to write. Really boring. K1 times C squared, and then we have I times A1 star A3 and then A2 star e to the minus I delta K times Z plus the complex conjugate. Yeah? And of course we can delete a few things. No. This one cancels. This one here cancels. What else? Yeah, that's it already. Yeah, we can of course then write k as n times omega divided by c, and then more cancels. Yeah, so more will cancel. So what we do is, yeah, so we do this actually, is n1 times omega 1 divided by c. And then we find epsilon 0 times the effective nonlinearity times omega 1 times I, and just copy this here. Yeah? A1 star, A3, and A2 star, plus this factor with the phase or phase mismatch. And yeah, and this can be simplified. Yeah, so we have the complex conjugate here. So this means that we get the imaginary part here of the expression in brackets. So what we then find is that the change of the intensity with respect to z is equal to minus 2 times epsilon 0 times the effective nonlinearity times omega 1, and then the imaginary part of A3 times A1 star times A2 star, and this phase mismatch thing here. Okay. Yeah. So all trivial calculations, but it has to be done. And it has not just to be done for A1, but also for A2 and A3. Yeah? So we write down same procedure, for the derivative of I2 and the derivative of I3. Yeah? And what we get is dI2 over dz is equal to minus 2 times epsilon 0 times the effective nonlinearity times omega 2, as you would guess, times the imaginary part of A3 times A1 star times A2 star times e to the minus I delta k times z. Oh, that's interesting. Yeah, this is just the same as above. The only difference is that we have here omega 2 instead of omega 1. Right? And then guess what we get for intensity 3? Well, there's one difference. We have a plus sign. But the rest is the same. Just omega 2 changes into omega 3. But we have this here. Yeah. So what we will do next is the following. So we now add di over dz. What do you expect? If I add all these three, yeah, so what I do is the following. Yeah, so I take the sum from all these things here. What do you expect as a physicist? Yeah?
Should be 0.
Should be 0. Yeah, should be 0. Why?
Because the total number of photons, so to say, the total energy of the photons is conserved.
Yeah, okay, the total energy of the photons is conserved, right? So if no photons are, if there's no absorption, then it may be that we take 2 photons from A1 and A2 and convert them in another photon, but it has higher energy, right? We expect energy conservation there, right? And this is what we get here. Yeah, so what we get is di over dz, which is, of course, just this sum. Yeah, so the intensity, the total intensity is, of course, I1 plus I2 plus I3. And this is equal to -2 times epsilon 0 times the effective nonlinearity, and then omega 1 plus omega 2 minus omega 3, and then the imaginary part of this thing here. And we know, of course, that this here, that this sum here is equal to 0, right? So what follows here is that the change in intensity in a non-absorbing medium is equal to 0, right? So the intensity is constant, yeah, as expected. Because there's no absorption, because of no absorption. So what we could further say is actually that the change of the intensity, if we divide the intensity through omega, yeah, intensity 1 through omega 1, then we find that all these changes are equal. Of course, the third one, omega 3, has a different sign. Now this is 2 here. Yeah? Also, this makes a lot of sense, because this literally says, so you always have to consider, what does an equation want to say to me? And this equation wants to tell you that if you destroy one photon omega 3, or if you create one photon omega 3, you would destroy one in omega 2, in omega 1 and in omega 2. Yeah? Yeah, we didn't talk about photons here, yeah? So we are not doing quantum optics, we are just doing kind of classical optics, nonlinear, so. But nevertheless, it gives us a, it reproduces the result that we know from quantum mechanics. Yeah, so the interpretation, let's write down the interpretation. So the rate at which photons at frequency omega 1 are created equals the rate at which photons at omega 2 are created, and this equals the rate at which photons at omega 3 are destroyed. Yeah, so these Manley-Rowe relations, you might say, what a big name for this trivial thing, right? But actually, if you think about an nonlinear electronic circuit, then things are probably not as obvious as they are in optics. Okay, well, that's it for today. I don't want to start with a new chapter today, so we close a little bit earlier. Sometimes I close a little bit later, so this compensates things. What we'll do next time is to look at less trivial approximations as we did today. So, for example, we would say, well, one of the fields is strong as compared to the other fields, and but the second field is weak. Yeah? So the second input field is weak, and then we would look what happens there. So such approximations we'll do. They have a special name, undepleted pump approximation. Yeah, and again, there will be some nice insights. See you next Monday.